All right, section 9.4 is an interesting one. It's called the Binomial Theorem, and it's really a way to expand binomials using concepts of combinations. And those combinations present themselves in a bit of a pattern here. So this first part is called Pascal's triangle, and it was discovered in the 13th century. Each number in that triangle is a sum of the two numbers diagonally above it. So every time you start a new row, you start with a number 1. And by the time we get to row 2, we have this gap in the middle below these two 1s. And so this one and this one create 2. And then the 3 in row 3 comes from here and here. So you add the 1 and the 2 and you get 3. And you do the same thing over on this side. And so we end up with a symmetrical table. We always have 1s on the outsides of each row, and the insides are generated by looking at the numbers above those slots. So since I always start and finish with a 1, I can fill in the ends of row 4, and then to get the first number I just need to look above it. I have a 1 and a 3, so the total is 4. And then I have a 3 and a 3, so the total is 6. And again, 3 and 1, total is 4. So we'll have symmetry on each side of each row. Each row will start with a 1, and the second number of each row is going to be the row number. So whatever row I'm on, that tells me what the second number is going to be. All right, so row 5, we have a 1 on the outside, a 1 on the end. We have 5 here, and symmetry tells us 5 here. 4 and 6 makes 10. 6 and 4 makes 10. And so that's how the triangle gets generated. All right, we can then extend that to get further rows. We can do as many rows as we feel like we need. All right, so to expand the binomial in this second second section here, a plus b quantity cubed, what I would need to do using algebra techniques is to write a plus b times another a plus b times another a plus b. And so we could just multiply the 2 on the end. So I could say that this product is going to make a trinomial. It's a times a. It's a times b and another a times b on the inside, so 2 ab's. And then b times b is b squared. And then I still have this a plus b. And then when I multiply this, I'm going to distribute, so I get a cubed. A times 2ab is 2a squared b. A times b squared is ab squared. And then I go over here and start with the b. And b times a squared is a squared b. B times 2ab is 2ab squared. And b times b squared is b cubed. So just combining like terms, I have my a cubed first. The a squareds would be this, 2 of them here and 1 of them here, so there's 3 a squared b's. The ab squareds, there's 1 here and there's 2 more here, so 3 ab squareds. And then there's a 1 of the b cubes. And that would be the result there. So what do we notice about the coefficients? Well, if you look at Pascal's triangle, row 3 of that triangle is the coefficients of this expanded binomial. So we can say that they are the coefficients spelled that wrong. They are the coefficients, oh boy, come on, of row 3. Okay, so what's going to happen in the binomial theorem, and this long formula here is not really going to be necessary for us. What it's saying is you do n choose 1, n choose 2, n choose 3, and so on to develop those coefficients, but those coefficients are just going to come from Pascal's triangle. So what we need to do is look at the exponent, and whatever the exponent is, that's what row we're looking at. So the coefficients come from row n. Okay, so whatever n is, whatever that power is, that's where we're going to look in Pascal's triangle. So for example 1 here, use the binomial theorem to expand each binomial. So you have a card available to you today, and you can use this card whenever you need to. And what we're going to do with each of these problems is apply that concept of using row n to get these coefficients. Now the other thing we have to look at, if you look at the beginning of this formula here, the first term is a to the n power. So that means that whatever binomial power I'm looking at, I'm going to also have that same power on the first variable, or on the first term. And then the second term is going to start at exponent 0. In the second term, whatever the first term of the binomial is 1 power lower than what I started at. And the second term is going to be to the first power. In the third term, I go 2 lower than what I started at, and then the power is 2 on the second part. So the first part exponents are decreasing from whatever number I'm starting at, and the second term's powers are increasing from 0. So let's see if we can write this out. So for number 1, it's a power of 5. So I'm looking at row 5, and row 5 goes 1, 5, 10, 10, 5, 1. So those are the coefficients that I want to use. So my first term is going to be starting with a 1. I'm going to look at this first part and raise that to the 5th power. And I'm going to look at the second part and raise that to the 0 power. So the first term will always contain the same power that you started with, and will contain a 0 power for the second part of the binomial. All right, term 2, it's going to start with a 5. So I'm looking across that row of the Pascal's triangle. So it starts with a 5. I have an a, and I go 1 power down. And then I have a b, and I go 1 power up. All right, term 3, it's going to start with a 10. Put an a, 1 power down. Put a b, 1 power up. And I'm just going to continue this. Fourth term is another 10. A is 1 power down. B is 1 power up. Fifth term's a 5. A is 1 power down. B is 1 power up. And the sixth term is a 1. A is 1 power down. And B, down to 0. And B is 1 power up to 5. Okay? Now look across here before I simplify this. Every single term, notice what the exponents do? 5 and 0, 4 and 1, 3 and 2. They're always adding up to the same power that we have in the original problem. So that's one way you can check your work here, is does every pair of exponents add up to the same as what we started with? All right, so all the 0 powers are going to equal 1, so they're just going to drop out. And if I have a 1 in front, I'm not going to bother to write it. So it's just a to the 5th for the first term. Then I have 5a4b1, so I'll just write 5a4b. 10 a cubed b squared, 10 a squared b cubed. I'm just cleaning it up here, that's all I'm doing. 5a b to the 4th, and that 1 can go and the a to the 0 can go, so just b to the 5th. So that last line should just be a matter of cleaning up your work. Okay, so pause the video there and see if you can figure out how to do number 2. Okay, so for number 2, I'm using row 7. So I'm going to start with a 1. I'm going to start with an x to the 7th and a y to the 0. Because remember, I always start with the same exponent as in the problem, and then the second variable gets a 0 power. All right, moving across the row, it's 7. It'll be x6. It'll be y1. The next number is 21, and it's x5, and it's y2. And then we have 35. We have x4 and y3, another 35, x3, y4, and all of these are adding up to 7 every time I do one. 21, x squared, y to the 5th, 7, x to the 1st, y to the 6th, and 1, x to the 0, y to the 7th. Okay, so to clean this up, all I would need to do is convert this first term to x to the 7th, the last term to the y to the 7th. Oops. Okay, and all the other ones are going to stay what they were. So just check that you did that correctly, and we'll move on to the next page. Okay, so I've recopied this triangle here, but again, you have it in front of you on the cardstock. I'm going to skip over the 10th power only because I'd have to create 3 more rows in this triangle. I don't really feel like doing that right now. So, and it's a lot like the first two with just 2 variables, so I think we can skip that one. Let's go to number 4. So number 4 is using row 6 because it's a 6th power. So let's start off with a 1. We're going to do x to the 6th, and then the second term's not a variable this time, so we'll put -3 to the 0. So every time I write a term now, it's going to have an x and a -3. Okay, so the second term, and notice I used parentheses here. I'm always going to use parentheses if I have a number value there. Second term would be 6, and it's going to be x to the 5th, and it's going to be -3 to the 1st, because I need to increase the second term's exponent. Third term is a 15. It's going to be x to the 4th, and -3 squared. Then I go to 20, working across row 6 there. So x to the 3rd, -3 to the 3rd, right? Because they need to add up to 6, and this -3 power is increasing. Then I have a 15 again, and it's x squared, and it's -3 to the 4th. I have a 6, and then x to the 1st, and -3 to the 5th. And finally a 1, and an x to the 0, and a -3 to the 6th. Alright, I am never going to take a shortcut on this first row when I'm doing one of these expansions, because I always want to see the powers add up to the right number. So if I have a 0 power, I'm not going to skip that term. If I have a first power, I'm not going to skip writing the 1. I always want to see those powers. And also I do want to make sure that every number I use in this expansion formula does get into a set of parentheses. Alright, now I'm going to go turn by turn and just clean it up. So -3 to the 0 would be 1, times 1 is still 1, so the first term is just x to the 6th. Alright, in the second term, -3 to the first power is a -3, and then times 6 is -18, so I don't copy that plus sign down. I check the numbers first to see what kind of sign I should use. And so I put a -18 and then x to the 5th. Third term here, -3 squared. Any negative number that I square is going to become positive if there's an even power. And so that's +9 times 15 is going to give me 135. And that's x to the 4th. And I'm doing that the same way every time I do a new term. I just want to calculate whatever numbers I have and then go there. So -3 to the 3rd is going to be a -27. When I multiply that by 20, I get -540. And that's x cubed. Moving along here, -3 to the 4th is positive because it's an even power. 81 times 15 is going to give me 1,215. X squared. Second to last term here is going to be a negative again, -243 when I raise this to the 5th power, times 6 gives me a total of -1,458. And that's just x to the 1st. And lastly, this x to the 0 is nothing, it's just going to become 1. -3 to the 6 becomes positive, and 3 to the 6th power is 729. Okay, so you notice the signs, they're alternating, and that's because the types of powers I'm using are alternating. So even, odd on the -3s, even, odd, even. Every time I have an even, it's a plus. Every time I have an odd, it's a minus. So it's just going to alternate. All right, let's look at another one, number 5. So I'm in the 7th row, and let's see what I get. So I'm going to start with a 1. The 2m will go to the 7th power, and the n will go to the 0 power, because it needs to add up to 7. And again, I'm putting this in parentheses because all of this needs to get the 7th power. All right, don't take any shortcuts, not on the first line. 7 times 2m to the 6th times n to the 1st. Powers add up to 7. I'm on the 2nd slot. 3rd slot should be a 21. Okay, I have 2m going down 1 power to the 5th, n goes up 1 power to the 2nd. Then I'm at 35. So I have 2m to the 4th. I have n to the 3rd. Another 35. 2m to the 3rd. N to the 4th. Now we have a 21 again. 2m squared. N to the 5th. A 7. 2m to the 1st. N to the 6th, and one last term if I can squeeze it in. 2m to the 0, n to the 7th. Okay, good. Fit it all in there. All right, so looking across here, I see every time I have parentheses here, the m is going to get the exponent, and the 2 is going to get the exponent as well. So I need to do 2 to the 7th power here, and that gives me 128. There's nothing to multiply by here, that's just 1, so it's m to the 7th. Okay, second term. I need to do 2 to the 6th and multiply by 7. Alright, so if I do that, I get 448. Also m to the 6th and n to the 1st. Third term, 2 to the 5th times 21. And all that can be done on a calculator. You do not have to do this in your head. 672, m to the 5th, n squared. Next term. 2 to the 4th times 35, 560. M to the 4th n cubed. 2 to the 3rd times 35, it's 280. M to the 3rd, n to the 4th. All right, and then I have 2 squared times 21, it's 84. M squared, n to the 5th. 2 to the 1st times 7 is 14. M to the 1st, n to the 6th. And then 2 to the 0 is nothing, it's just 1. M to the 0 is 1, so just n to the 7th. Alright, hopefully you're starting to get the hang of this by doing your expansion using the triangle and proceeding. Okay, so I think we can skip 6. Skip 6 works exactly like 4. Oh, with the exception of it's positive 2. So you'll just put parentheses 2 each time. You won't have to worry about oscillating signs. Let's jump down to number 7. Number 7 is back to row 5 of our table. What I want to do is just drag this card down a little bit so I can see it a little better. Okay. So I have 2 terms that both have numbers, so this will get a little bit messier, I guess, but it's only 5, so I'm dealing with fewer entries. So I start with a 1. I have 3p to the 5th power and negative 2q to the 0 power. And they're all going to look like this. I have a 5, I have a 3p, 4th power, negative 2q, 1st power. All right, pause here, try to write out the rest of it, and see if you match up. Okay, we should have a 10, 3p to the 3rd, negative 2q to the 2nd. It's another 10, 3p to the 4th, negative 2q to the 1st. All right, plus 5. 3p to the 5th, negative 2q. I feel like I missed something here. Ah, right in here. Yes, these powers are incorrect. Let's see if we can fix those. All right, so I want these. I'm going down by 1 here. So 3 should become 2. 2 should become 3. Now I'm back on track. So this one would be a 1, and this is a 4. Yeah, now we're good. And then a 1 for the last term, 3p to the 0, negative 2q to the 5th. All right. So 0 power doesn't matter. 3 to the 5th is 243. I have p to the 5th. Next one down, we've got to do 3 to the 4th times negative 2 to the 1st times 5. Well, that negative 2 to the 1st is going to become negative, so the whole thing is minus. And if I multiply 5 times 3 to the 4th times 2, I'm going to get 810. And it's P4 Q1. Okay, now I go 10 times 3 cubed times 2 squared. Negative squared is positive. 10 times 3 cubed times 2 squared. And that's going to come out to 1080. Get my exponents right. Okay, 10 times 3 squared times negative 2 cubed. So that's a minus because of the odd power on the negative. And that will multiply out to 720. P squared q to the 3rd. Okay, 5 times 3 times negative 2 to the 4th, even power, so it's a plus. It keeps on switching as usual. And that works out to 240. PQ4. And lastly, 3 to the 0 is 1. P to the 0 is 1. Negative 2 to the 5th is negative. And it's 32. Q5. Okay, so I think we get the idea there. Let's go over these last few observations and then we'll be good to go. All right, the total number of terms is always going to be n plus 1. And the reason for that is we always start with the exact n, right? The first exponent is always n, and then we work our way down to 1, and that would be n terms, and then we have this extra term where we let it equal 0. So that's why it's n plus 1 terms. The exponent of a will always be n, the exponent of b, and the last term will always be n. So first term starts at n, a starts at n, b ends at n for their powers. Okay, the exponent of a will decrease by 1 from left to right. The exponent of b will increase by 1 from left to right. The sum of the exponents in each term is always n. We saw that, 5 plus 0, 4 plus 1, 3 plus 2, and so on. And the coefficients are symmetrical. And they follow the nth row of Pascal's triangle. All right, now you will be able to use your card whenever you're doing a binomial expansion problem, but in the future, if you ever get stuck without it, it's really easy to make this triangle, right? I just start with a 1, I put 2 1s around it, put another 1, I put a 2 in the middle, and another 1, and you always can remember that the row number tells you how many things there are supposed to be. Row 3 should have 3 parts. Row 4 should have 4 parts, so 1 and 1 on the ends, 3 and 3 in the middle. So you can make your own triangle whenever you need to. It isn't hard to do. Okay, that should do it here. So go on to the next section, and next time you see one of these expansions, you will be good to go.